Hello? Okay. We'll go ahead and get started now. Good evening. My name is William Seelig. Welcome to the U.S. Geological Survey. I work for Science Information Services. Glad to see everybody here for our January public lecture. Before I introduce this evening's speaker, I'd like to remind everyone about our February lecture on scanning and electron microscopes. You can pick up a flyer at the back table there. And I hope to see everyone here on February 23rd for that lecture. For tonight's lecture, the title is Unusual Sources of Tsunamis from Krakatoa to Monterey Bay, presented by Eric Geist. And a little bit about Eric. He is a research geophysicist with the Pacific Coastal and Marine Science Center of USGS, where he's worked for 32 years. Throughout his career, he's focused on computer modeling of geophysical phenomena, including the physics of tsunami generation. Eric has authored numerous journal articles, including a Scientific American article on the devastating 2004 Indian Ocean tsunami. Eric received his bachelor's degree in geophysics from Colorado School of Mines and his master's degree in geophysics from Stanford University. As always, after the presentation, we'll have questions from the audience. Just please hold your questions until afterward. And please welcome Eric Geist.
Thank you, Will. Can everybody hear me okay? All right. Great. Thanks for coming out tonight and listening to about tsunamis here. As probably everybody knows, is that most tsunamis are caused by earthquakes. We've had the devastating 2004 tsunami in the Indian Ocean, and of course a 2011 tsunami in Japan that destroyed the Fukushima nuclear power plant. What I thought I'd do for the public lecture today, though, is look at tsunamis not generated by earthquakes, by all these other sources, which I think is kind of an interesting line of research. And what we're going to do is look at probably the most famous of these non-seismic sources, Krakatoa, that erupted in 1883. And I'm going to frame the talk around Krakatoa. We're going to pose two problems. The first problem is looking at the tsunami that hit Jakarta, very close to where the volcano erupted. And then we're going to take a step back and look at basics of tsunamis, how they're generated, the type of waves tsunami waves are, and importantly, tide gauge measurements. These are, we're going to mostly be looking at case studies. So tide gauges actually give us the most important instrumental data for tsunamis. Then we're going to look at different types of non-seismic tsunamis, volcanic tsunamis, where we're going to try to answer our Krakatoa problem number 1. And then post-Krakatoa problem number 2, that is the San Francisco tsunami, and what's that all about. We're going to take a break from problems and look at briefly at asteroid tsunamis, landslide tsunamis, and then atmospheric tsunamis, meteorological induced tsunamis, and then pose an answer to Krakatoa problem number 2, and then end up with a kind of interesting summary of all this. So Krakatoa. The activity in Krakatoa actually started months before the big eruption. Started in May of 1883 and culminated in this huge explosion in August of 1883. It destroyed 2/3 of the island. This is a map of the island before the eruption, shown here. And after the eruption, 2/3 of this was gone. The dashed line represents the crater, what was left of the island under the water. And activity at Krakatoa continues today. Now, Krakatoa is known for a lot of things. One is it generated a pressure wave that was recorded all the way around the world. The pressure wave actually traveled 3.5 times around the world, was recorded on virtually every barometer in the world. It produced the loudest sound ever recorded. The sound was heard 4,800 kilometers away, believe it or not. And it produced one of the most destructive and deadliest non-seismic tsunamis, and it turns out the most complex, and I had no idea how complex it was before I started putting this talk together. So there's a lot of things going on with Krakatoa. So we'll start from the beginning. Where is Krakatoa? Krakatoa sits in this body of water between Sumatra, the island of Sumatra in Indonesia, and Java here in the Indian Ocean. So we're going to zoom up in this place. This body of water is called the Sunda Strait. This is a map not up to USGS standards, but this is land here, Sumatra and Java here. What's contoured is the sea floor. Krakatoa, what's left of Krakatoa, sits right here. This little passage is kind of like the Golden Gate. The tsunami amplitudes die off pretty quickly as it gets into this body of water. And this is where Jakarta sits here. And that's where our tide gauge station is. That's what we really want right there. But these numbers are tsunami run-up, how high the waves got on shore following this event. These numbers are from a very comprehensive report soon after the event, published by the Royal Society of London. But since then, some other surveys came out and determined that the highest run-up of a tsunami from Krakatoa is 41 meters. So that's definitely a huge tsunami. I could probably consider it a mega tsunami, although we'll see bigger tsunamis later on in the talk. So that's where we're at. So what we're looking at is what is the exact mechanism that caused the tsunami. Volcanoes tsunamis are kind of interesting because there's a number of different mechanisms that can cause the tsunami listed here. We'll be looking at a sampling of these, and then we'll add to this a number of other non-seismic sources for tsunamis. Some may be familiar and some may be unfamiliar to you. We can group these into tsunamis occurring in the atmosphere, or meteorological tsunamis, and landslides, of course, can cause tsunamis. What we're going to be talking about here mostly in this talk is the physics of tsunami generation. And what's important is knowing where these sources are relative to the water's surface. And then, of course, we have earthquakes, which are most common. They generate about 70 to 80% of the tsunamis that are in the catalog or that have been recorded. So we can't forget earthquakes. So we're all on the same page. I'm going to go through the life of a tsunami using an earthquake source. So what do you need to get a tsunami generated? Something that generates, that's able to push up and down the entire water column. The other thing you need is something that's very wide. It has to be wider than the ocean is deep. And optimally, it has to be 3 times wider to generate the very long waves necessary for a tsunami to propagate all the way across the Pacific Ocean, for example. So that's what you need. Once you generate this massive instability in the water column, it's not going to want to stay in one place. If you're looking in cross-section, you're going to have the transoceanic tsunami propagating out into the deep open ocean. And then you're going to have the local tsunami, of course, propagating in the opposite direction. These waves gradually evolve. When it gets into shallow water, the tsunami actually slows down. The wavelength decrease, and in order to conserve this massive volume of water, the amplitude has to increase. This is termed shoaling amplification. So, and this is a pretty dramatic effect. You can have a 1-meter tsunami in the deep ocean transform to a 30-meter tsunami on shore, as we've seen with the 2004 event. So when it hits the shore, that's called tsunami run-up, and it comes in like a fast-moving tide. Run-up also specifically refers to the vertical height of the wave, the maximum vertical height. In inundation, another term I'll use is the horizontal extent of flooding, so it's a horizontal measure. Important thing to remember is that tsunami waves, there's not just one tsunami wave, but they last for many hours. There are many tsunami waves. So to summarize here, the 3 things you need to keep in mind for a tsunami are you need a source that generates motion of the entire water column, up and down, vertical motion. You need a very wide source relative to the water depth. So if your water depth is very shallow, you don't need as wide of a source. And then another thing, you need a fast source, something faster than the speed that tsunami waves move. But as we'll see, not too fast. This is kind of new research. If it's too fast, it also doesn't generate a tsunami. So our data comes instrumentally primarily from tide gauge records. Now, this is a very old tide gauge record from San Diego. Tide gauge records show the height of the sea surface as a function of time. So these, I think, are hour marks on here, time along here. It's attached to a clock. This drum is attached to a clock. And in here you can see the high tide and the low tide occurring twice a day. But then you see these interesting fluctuations on top of the tide. So the people that installed this were wondering, what the heck are these fluctuations? We filtered out the wind waves. I don't know what these are. Remember, this is 30 years before the invention of the modern seismometer. So, in the weeks following the installation of the West Coast tide gauges, which was San Diego, San Francisco, Astoria, Oregon, this was all brought about, as you can imagine, by the gold rush, so you need to know where the tides are. A person by the name of Lieutenant Trowbridge heard about an entire fleet of the Russian Navy being sunk by a tsunami in Japan in 1854. So he thought, okay, this tsunami might have been recorded in San Francisco. They knew the speed of tsunamis back then. It's by this formula I'll refer to, square root of GH. G is gravitational acceleration, 9.8 meters per second squared. H is the water depth in the ocean in meters. So when you multiply them together, take the square root, you get a velocity of meters per second. So they knew how far Japan was from San Francisco and San Diego, and sure enough, the times matched up perfectly. So this was the first recording of a tsunami on the U.S. West Coast. Now, San Francisco has the fame for having the longest record of tides in the entire United States, and it's recorded 57 tsunamis since then. These were the first ones, though. So why all the fuss about tide gauge records? Scientifically, there's a lot of information in tide gauge records. So here we're going to look at more recent tide gauges from the 2004 Indian Ocean tsunami. There's two of them here. So again, time along horizontal axis and sea surface amplitude here. In this case, here's high tide. It's coming in Phuket, Thailand, and low tide over here. So the Maldives are located to the west of the big magnitude 9.2 earthquake in the Indian Ocean that caused that large tsunami. Phuket, Thailand is to the east. Okay, just keeping that in mind. So if you know the time of the earthquake, the arrival time of the tsunami is going to tell you where the source of the tsunami is located because we know the velocity. If you know we know it can read off the amplitude of the first waves, that'll give you an idea of how much the seafloor moved up and down. Then the polarity of the waves, importantly, tell us which way the seafloor moved, up or down. Now, if you take this slice from Life of a Tsunami, if you recall, it's moving up initially in the transoceanic tsunami towards the Maldives, and that's what we're seeing over here. In Phuket, Thailand, it's moving down first, and that's what we're seeing over here. So you get some idea of what the seafloor was doing right from the start there. And finally, the period of these first waves tells you how wide the source is, or the horizontal dimensions of the source. So we can use a lot of information from tide gauge records. If you back out the tide, you get something that looks like a seismogram. We call them merograms, actually. So on to our four categories of non-seismic tsunamis, volcanic tsunamis. We're going to just look at Krakatoa, so unfortunately I don't have time to look at some of these others, so we're going to take flank failures and volcanic earthquakes off. We're going to look at first volcanic explosions, then pyroclastic flows, I'll explain what those are, and then caldera collapses. So this is kind of how a volcanic eruption evolves. First we have the explosion in the case of Krakatoa. The explosions are powered by the upward thrust of expanding gases in the magma chamber here. It sends off a huge column of ash and gases into the upper atmosphere. And importantly, and maybe not as well known, is a shock wave coming off the volcanic explosion. I'll term this either as a shock wave or pressure wave or maybe acoustic wave if you can hear it. A lot of times the higher frequencies will fall off, so when you're recording this around the world, it's actually termed an infrasonic wave, and a lot of people are recording these type of waves around the world with infrasonic sensors. And if you cover this explosion up with water, the initial motion of this would be in the up direction. Hopefully that makes sense. And they're rated similar to a magnitude scale for earthquakes. It's called the Volcanic Explosivity Index. The person that came up with this index is one of the authors is from the USGS, Chris Newhall. So Krakatoa is over here, VEI of 6. It's not the largest explosion in history. That occurred in Mount Tambora, just to the to the east of Java. But it's certainly one of the largest, and you can see some of the other historic eruptions up here. But then you look in geologic time here, we have close to us, we have Crater Lake, of course, and Long Valley caldera with much larger explosions going on. So that's volcanic explosions. Pyroclastic flows. Pyroclastic flows are to be distinguished from lava flows. Pyroclastic is kind of a broad term that includes rock, gas, ashes. But here in this nice cartoon from the USGS, the volcanoes group, you can see they can move very quickly from the top of the volcano and down and do a lot of destruction in their path, and they can enter in the water. So we've had, in particular, 2 scientists at our volcano observatories studying how pyroclastic flows enter into various water bodies, lakes and oceans. Chris Way-Thomas at the Alaska Volcano Observatory and Joe Walder at the Cascades Volcano Observatory. And pyroclastic flows are really interesting because you have this really light, low-density layer here that isn't going to go in the ocean. It floats right on top of the ocean. And this was actually observed from Krakatoa. But then you have this heavier material that's splashing into the zone and then eventually causing this coherent wave, which is what we're interested in. It's going to propagate outward from the volcano. And that also is going to start in the up direction. And then finally we have our caldera collapse. When large volumes of magma are erupted over a short period of time, structural support of the crust above the magma chamber is lost, and then the ground surface collapses downward. So if you have water over this, the initial motion of the water is going to be in the downward direction. Now, that's the volcano. In terms of hydrodynamics, something else is interesting is going on here. So this is termed in physics a monopole source. So most of these unusual sources are monopole sources. It's just going down in one direction only. The earthquake, if you remember, was going down and up. This one's just going down. But as the waves propagate away from this monopole source, they bounce back up, and they'll continue to do this. They'll oscillate in the source. So you have these waves propagating outward, but then you have this oscillation going on right at the source zone, far in time after these waves have left the source region. So to show you what this might look in a simulation, this is a caldera collapse from a volcano off the southern tip of Kyushu Island. So here's Japan, here's the island of Kyushu. Kike volcano erupted 5300 BCE. So what we're showing here is in map view. Again, not a great map, but the red is coastline of Kyushu here, and these are snapshots in time. So we're starting at 12 minutes and going along here to 96 minutes. Here is our caldera collapse. It generates this big hole in the ocean, a very strong negative wave, but then soon after that we get this positive wave here. That's the wave that's going to run ashore and cause some inundation to the islands around the volcano. So those are caldera collapses. So let's go back to Krakatoa. And to get oriented again, here's Krakatoa. We're interested in this tsunami that's going towards the Jakarta tide gauge station. Here's where we can use some of that information from the tide gauge. Now, here's the original tide, or a copy of the Jakarta tide gauge record. It's clipped here. These tide gauge stations were not designed to record the full extent of some of these big tsunamis. But you can see that the initial motion from the tide gauge record is in the up direction. So that means we can exclude the caldera collapse mechanism. It's also coming in a little late there. So we're left with the pyroclastic flow and the volcanic explosion. Now to get these larger run-ups, especially that 41-meter run-up here, it turns out that the pyroclastic flow is not going to do it. You need a volcanic explosion. And there's still some controversy about this, but I think that's more or less a scientific consensus right now. So in the near field, near the volcano, you needed the volcanic explosion to generate the tsunami. So, as I mentioned, the air pressure wave from the volcanic explosion was recorded all around the world. But interestingly, we have these tide gauge records from all around the world recording tsunami-like waves. Okay, so these tide gauge stations, so these are the ones that recorded these tsunami-like waves from Krakatoa are shown by the black circles here. The ones in the Indian Ocean are probably from that volcanic explosion, just typical tsunami waves. But then we have the interesting records from the English Channel, from Panama, from Alaska, from Hawaii, and San Francisco. And here's that record from 1883 in Sausalito. The San Francisco tide gauge station kind of moved around. And we went from Fort Point, or from Presidio to Sausalito to now it's in Fort Point. But here are these waves. Now here's when we're expecting the tsunami to come in from Krakatoa. We know this pretty well because it just depends on the water depth, so we can calculate that with pretty good accuracy. What it has to do is, when we know this from the 2004 Indian Ocean tsunami, it has to come around Australia, go into the South Pacific, and then come up all the way into the Pacific to San Francisco. These waves right here, which are the biggest waves from Krakatoa recorded at the San Francisco or Sausalito tide gauge station, are coming in 5.5 hours earlier, so way earlier than what we were expecting the tsunami to come in at. So that's our problem number 2. So we're going to leave that there, look at a little bit on asteroid tsunamis, and probably what comes to mind of asteroid tsunamis is Chicxulub impact crater, which occurred right off the Yucatan Peninsula on the Campeche Shelf. This occurred at the Cretaceous and Paleogene boundary, period boundary in geologic time. And it was probably the triggering event for the die-off of the dinosaurs, of course. But what we're interested in here is the tsunamis generated from this impact. Geologic deposits that look an awful lot like tsunami deposits have been found all around from Mexico into Texas. This is probably the most famous one near the Brazos River, around the Gulf Coast, in the Atlantic, in the Caribbean. So the question here is, did the impact itself generate the tsunami, or did it must have caused a huge amount of ground shaking. Did that let loose a lot of landslides in the Gulf of Mexico, and did those landslides generate the tsunami? So that's our question. We didn't have a tide gauge station, unfortunately, in the Cretaceous. But we did have these geologic deposits. We can glean some information from those. And we can look at model simulations. So this is, we are fortunate to have this. This is the latest type of asteroid simulation. This is coming from courtesy of Dr. Daryl Robertson at the NASA Ames Research Center down in Mountain View. This is brand new simulations, and these are pretty sophisticated simulations, so I'm going to have to do a little bit of explaining for these. So what we have here is an asteroid of very large size coming directly vertical, so it's coming straight up and down into the ocean. Now, because that's, let's see if I think I messed this up here. Okay, so here the asteroid hits now. So we're only seeing 1/2 of the simulation. Because of symmetry of the problem, we only have to compute 1/2 of the simulation. So in your minds, picture a mirror image of this on the left-hand side and try to piece them together. So just realize we're only looking at 1/2 of the simulation. This gray is the solid Earth. The blue is the water. The black is the atmosphere, okay? So the boundary between the black and the blue is our tsunami wave height, or wave height. I'm going to hold off on the tsunami part of it. This is the wave height. So here we're seeing this already, this huge splash in the ocean from the impact. The other information that's conveyed in these simulations is this color gradation here. Now these are essentially the pressure waves caused by the impact. So we have pressure waves in the ocean, there's pressure waves in the solid Earth that you can't really see, and a lot of airflow associated with the impact. So there's a lot of information in this. So I'll go ahead and continue it. Recall from this is another monopole source, so you're going to get this rebound right in the source region as waves start to propagate outwards, and it's going to kind of oscillate along here. See all these pressure waves bouncing back and forth. These are basically acoustic waves bouncing back and forth in the ocean. They're acting like a waveguide in the ocean, and a lot of this complex flow in the atmosphere. Now we're going to speed this animation on a little bit and see, okay, here are our waves, but remember from Life of a Tsunami, these waves are short. They're less than the wavelength of those waves from peak to peak is much less than the ocean is deep. So these are not tsunami waves. These are deep ocean waves akin to, they're very large amplitude, but they're akin to deep water swell, like you get on a fishing boat or something like that. The problem for a deep ocean impact, they're going to probably break at the continental shelf edge and really not do that much. So this is probably an anticlimactic part of the talk, especially for fans of the Deep Impact movie. Asteroids are not efficient tsunami generators, believe it or not. And I was talking to my postdoc after the practice talk, and he said, yeah, it's happening too fast. The water's almost behaving as a solid in this case instead of a liquid. So that was one of the new things, I think, coming out in the world of asteroid tsunamis. So now we're going to go on to landslide tsunamis. Here it's important to distinguish between landslides occurring above the water and those occurring below the water, and I'll show you why. Most of our case studies, all except one, occur in Alaska for good reason, because we have the glaciers retreating, leaving these unstable hillsides of the fjords, such that you can have these massive piles of rock fall into the deep water of the fjords. So a lot of these case studies are going to be from Alaska. First one we're going to talk about is Lituya Bay, which people here probably have heard of. There's, I think, a Discovery Channel program on mega tsunamis on this. This is on record for having the highest tsunami run-up in Lituya Bay. What people are probably less aware of is a similar event occurred just a year and a half ago in the Tanfjord in Icy Bay here. So to get oriented, here's Skagway, Juneau, Glacier Bay National Park is here, and Anchorage sits way over here. We'll look at a case that hasn't happened yet in Tidal Inlet in Glacier Bay National Park. And then in Valdez, this is going to be our case of a submarine landslide that was triggered by the magnitude 9.2 big earthquake off of Alaska that generated the tsunami in Crescent City. But we're just going to be looking at the landslide tsunami in Port Valdez. So let's start with Lituya Bay. Let's see. This is a famous USGS photo looking from the ocean into the bay. Common with these type of mega tsunamis is you see that all the vegetation and trees just sheared off right through here inside the bay right here from the tsunami in the aftermath of the tsunami. The rock fall actually occurred just around the corner here. So this view is looking up towards this direction where the glacier, Lituya Glacier, sits here. So this big pile of rocks fell into the ocean, and this nice simulation from Professor Juan Jarillo, see if I can get that started, shows exactly what happens. You have this big splash going in here, and then this wave go up to and he's able to exactly match that run-up. I don't know how he does that, but 524 meters, so that's a huge wave, of course. That swept over the nose of this ridge, and this ridge is right here. So that's that kind of tsunami. Again, something that's very similar just happened in the Tanfjord, captured the attention of a lot of tsunami scientists that have gone up here. These photos are courtesy of Dr. Brentwood Higman, who's done a lot of work up there. Here's our big landslide occurring next to a glacier here. Fell into the water, stripped a lot of the vegetation, even far from the landslide's way back here, so the vegetation's still affected way this far into the fjord, and satellite views of before and after of what it looked like after the tsunami. This tsunami was 192 meters, still a pretty big tsunami. In fact, the fourth largest tsunami ever recorded. So now we're on to Tidal Inlet. Tidal Inlet is this body of water you probably never heard of. It's this really narrow body of water that sits off the western arm of Glacier Bay in Glacier Bay National Park. So if you venture in, if you're brave enough to venture into Tidal Inlet, you see this feature here. This is a landslide that has already slipped down the slope part way, not quite all the way yet. And it's been like that for a while. So our concern, of course, what if this huge body of rock were to fall into Tidal Inlet? What kind of wave is that going to generate? And this is that simulation. It's going to probably generate very large waves inside Tidal Inlet. What we were more concerned with are the cruise ships that go up and down in Glacier Bay and what the effect these kind of waves are going to have on the cruise ship. So you can see the waves are quite different as it goes into the deep water. They're longer waves, smaller amplitude waves, but still of concern, obviously. So now, submarine landslides. I hope to give you the impression that submarine landslides are a different beast altogether than landslides occurring above the water. So submarine landslides are also triggered by earthquakes. So what happens in a submarine landslide is that you have this big pile of rocks that fails and starts moving down the slope Where it fails, we call this the excavation region, and it's going to suck the water right down with it, so we get a negative amplitude wave. And then as these rocks move down the slope, it pushes the water up. So here we're going to get a positive wave. So this is a dipole wave, just like our earthquake, positive and negative here. Unlike earthquakes, though, this is occurring in much slower speeds than earthquakes happen a lot faster than tsunami speeds. This is happening at an unknown speed. This is the frustrating thing about submarine landslides is we have virtually no idea of how fast these rocks are moving underwater. We can tell above water, but underwater it's very little information. So we need other data, and often there's just not enough data to really understand these waves. So we're really good at mapping the aftermath of these landslides. This is off Santa Barbara from the Monterey Bay Aquarium Research Institute. But for tsunami purposes, we need to know the speed of these waves. And to demonstrate that point, we're going to have two experiments. One is we're going to have a landslide go off the continental shelf edge at 50 meters per second. The tsunami waves want to move at 200 meters per second. So we're going to start this and stop this a little bit here. So the landslide's underwater. We're seeing the surface of the water. Here's our landslide. It pushes up waves, but no more than it starts to push them up, the tsunami waves start to zip off really quickly. So they never build up to large amplitude. Now, if we have an experiment set up so that our landslide is moving at the exact right velocity, 200 meters per second, we're going to get very large amplitude waves moving in the direction of landslide motion. The wave coming back is still small, but it's complexly related to landslide motion. But concentrate on this. So this is what I'm going to call a coupled source. So that means that the source of the tsunami has to be coupled in terms of at the same speed that tsunami waves want to move in the ocean. That's square root of GH. Remember that. That's the only formula you're ever going to hear in this talk. Square root of GH. Okay, so here's our case for a submarine landslide in Port Valdez here. So like our caldera collapse case study, this is a case study for the 1964 tsunami in Port Valdez. This is map view of Port Valdez here, the eastern part of Port Valdez, 1 minute. These are snapshots again, 2 minutes, and then down to 6 minutes. Now here we have a really interesting point of observation. We have a ship, a freighter called the SS China, that was docked at the warehouse in the harbor of Port Valdez, located here. And by chance, somebody was taking a home movie pointed straight at the docks during the time of the earthquake and the tsunami. The landslide occurred right at the docks, right at the delta. It's called the Delta Front here. So you can go to YouTube, look for 1964 earthquake at Valdez, and you see this movie. It's actually pretty frightening to see this submarine landslide go on. But the PI for this project was Tom Parsons, and from those home movies, he was actually to find the position of the SS China, and we can use that to constrain our numerical models of the tsunami. So in colors, again, is the tsunami model. The blue represents the big negative amplitude over the excavation region. The red is the effects from the deposition region. The positive wave comes back towards shore, runs up into Old Valdez. By the way, Old Valdez has since been moved over to here, where it's New Valdez. The chain of renogram ran through some of the docks there, and then it got pushed to the southeast and then eventually broke free. But this was helpful in actually helping to constrain and verify our motions of the landslide movement. Otherwise, we had no idea. You can model the landslide itself, but that's a whole other complicated matter altogether. Okay, so I'll probably hear from this from any fellow scientists hearing, but as far as I can tell, we only have one instrumental record that's clearly a submarine landslide from a tie gauge station in the whole world. And it happens to be in our own backyard in Monterey Bay. So as I mentioned, most of the submarine landslide tsunamis are triggered first by the earthquakes, and the earthquakes are often offshore. So you have an earthquake tsunami and a landslide tsunami going on at the same time. And it's really hard to separate the two signals because they're about the same wavelengths. But here, of course, this is the Loma Prieta earthquake in 1989. It occurred on land, of course, along the San Andreas Fault. triggered some strong ground shaking, and a tsunami was recorded at the Monterey tie gauge station in Monterey Harbor. It produced about a 1 meter tsunami run-up in Moss Landing. So if you recall back at the beginning of the talk, what information we can gather from tie gauge records. First, the arrival time tells us where the tsunami source was located, because we had no idea where the tsunami source really was from this. You could tell, you could try to, from this arrival time, you can try and draw an arc to possible source locations, and not surprisingly, it has to be somewhere in Monterey Canyon. You didn't really need the tie gauge for that. But look at this polarity. This is the first upswing of the tsunami, so that means, if you recall, the deposition region, the tsunami, the landslide had to be moving towards the Monterey tie gauge station. That is, it's seeing the way from the deposition region from that landslide first. So that means the landslide had to occur on the north wall, somewhere along the north wall of Monterey Canyon. Now this part is a little less obvious, and hopefully it might be apparent in this animation. The landslide could also occur along the axis of the canyon. The waves from the deposition region are going to refract or bend towards Monterey, and actually this is the most probable source for that particular landslide. But this is an important record. This gives us an instrumental record, maybe the only one, of submarine landslide tsunami. Okay, now to atmospheric tsunamis. This is something new that I've been interested in, and it's kind of a joy to work with, because unlike submarine landslide tsunamis, we have a huge amount of data. It's a complicated process, but we have a lot of data to study these, and they don't tend to be they're not mega tsunamis. They're smaller tsunamis. They do some damage in small boat harbors. This is in the Balearic Islands off Spain. I'm going to call these Meteotsunamis, but you can see what they're called in all these different languages and cultures. Get an idea of where they usually occur. They usually occur in the Mediterranean, off Japan. In the U.S., they occur off mostly the U.S. Atlantic coast, the Gulf Coast. Florida's seen some recently, and of course the Great Lakes. So these surprisingly occur, in terms of the physics, very similar to submarine landslide. This is another example of a coupled tsunami. So what happens is you have a pressure jump. This pressure jump results in a deflection of the sea surface. It's termed the inverted barometer effect. Inverted because a positive pressure jump is going to result in a negative deflection of the sea surface and vice versa. So 1 millibar of pressure change is going to generate 1 centimeter of deflection in the ocean surface. Not big. I mean, that's not even hardly measurable on tie gauge stations. But if this is moving at the right velocity again, square root of GH, there's that term again, these waves are going to start to build and become significant. Then you can also have other sources of amplification. That's shoaling amplification, if you remember. They call it shelf amplification here, and some other sources of amplification. So if the conditions are right, these can be significant waves. The case study we're going to look at is from 2013, not that long ago, and I don't know if you remember, there was a significant weather system called a derecho. A derecho is basically just an organized squall line that's fairly extensive and moving quite fast. There's very strong winds associated with a derecho moving in the straight direction as opposed to a vortex like a tornado. So that's where derecho gets its name, derecho meaning straight in Spanish. So it's moving around 50 miles per hour across the northeastern United States. The National Weather Service stops these radar pictures right at the coastline, but of course what we want is a radar depiction offshore, and we have one, fortunately, showing this derecho moving offshore along this is the Atlantic continental shelf here, and this is the deep part of the Atlantic here. So there were 13 tie gauge stations in the Atlantic that recorded this Meteotsunami. I'm going to show a simulation. It's kind of an odd perspective. This is in the southeast direction. Here we go. You'll probably recognize some of these features. This is obviously Long Island, Delaware Bay, New Jersey, Cape Cod over here. This is the Hudson River, and as I'll show you, that becomes important. It goes along the continental shelf here, and right at the continental shelf edge, there's Hudson Canyon. Not as impressive as our Monterey Bay Canyon, but still, I guess by Atlantic standards, it's okay. So here's our simulation. So what I'm showing, I'm not showing anything in the atmosphere. I'm showing what's coupled with the water column. Here's our derecho coupled with the ocean, moving at a really the right speed for tsunami waves wanting to move. So as you can see, it starts to get larger and larger as it goes on there. At this point, the derecho hits the continental shelf edge. Now it's not moving at the right speed because these waves are moving a lot faster. This is deep water now. So these are decoupled waves moving out into the Atlantic. And interestingly, these waves are actually recorded in Bermuda and Puerto Rico from this particular event. Continue this along. What we now see is another decoupled wave. So here's the coupled wave. The derecho is still moving in this direction. This wave is from the continental shelf edge moving towards Long Island. But what we are actually really concerned with in terms of hazards, some people were knocked off the seawall in New Jersey here. And this reflection, I believe, is coming from Hudson Canyon. That's at least my interpretation of where this decoupled wave is a reflection from Hudson Canyon where it intersects the continental shelf edge. Let's see, what more to say about that? Oh, so interesting story. When we were looking at this event, we saw all these tide gauge records go off, and you can triangulate. You have 30 tide gauge stations, so you can triangulate where these sources were occurring. And we looked at it and say, okay, these sources must be occurring on the continental slope or shelf edge. These must be submarine landslide tsunamis. That's your first thought as a geologist, you know. So I think people actually even went out there looking for the landslide, but no, it was just an atmospheric, it was a Meteotsunami, did some damage, but they were coming from the continental shelf edge, but as reflections, decoupled waves, not from the coupled wave itself. I'll continue that along a little bit. Let's try to speed things up here. It kind of wraps around Cape Cod a little bit, and then there's a little bit of a summary of what's going on there. So another source for meteotsunamis are atmospheric gravity waves. These are in the very high atmosphere. This comes from airflow over, for example, a mountain range that disturbs the stable density layers of the upper atmosphere. Buoyancy forces try to restore the equilibrium. They overshoot, and oscillations set in, setting up these waves that can move at fairly significant velocities. The case study here, which I'm not going to show, is 2008 in Boothbay Harbor, Maine, that just had a 12-foot high meteotsunami that was fairly damaging inside the harbor there. So atmospheric gravity waves, these are just the waves in the atmosphere. We're not talking about the ocean yet. These are caused by airflow over mountains, over supercells, big thunderstorm systems. The air can flow over the supercells. And one other source of atmospheric gravity waves is directly from volcanic eruptions. So you can't see, well, it's hard to see these waves from the ground, but satellite's really good at envisioning these, they're termed lenticular clouds here. In this case, we had a large volcanic eruption in Chile in 2015, and satellite was able to capture these concentric rings of atmospheric gravity waves coming off from the eruption. So basically, the volcano is sending up this big column of ash way up into the stratosphere and mesosphere and setting off these atmospheric gravity waves. Now, you can probably guess we're getting to the answer to problem number 2 for Krakatoa. It turns out that the atmospheric gravity waves move a little bit faster, but importantly, they don't have to go over the ocean. They can go over land. They can go right over the Indonesian archipelago. They can go over Eurasia to the English Channel. So it turns out what we're seeing on our San Francisco/Sausalito tide gauge record are atmospheric gravity waves that are going at the right speed to couple with the water column and cause this tsunami-like waves in San Francisco, as well as Kodiak, Alaska, and Hawaii. This particular, we call it a mode, is going at the water velocity, I think, of the continental shelf water depths. So that's, I go to a summary now. Those are our 4 groups of sources, and I'm going to confuse everybody even further by scrambling these sources on this slide, but there's some method behind this madness, because rather than grouping them by geologic feature or atmospheric process, we're now going to group them by how they cause tsunamis. So first we have our our explosions shown here. We have our impact sources, which obviously includes asteroids, but maybe not obviously includes landslides perched on the sides of fjords and pyroclastic flows. For these, I kind of envision the efficiency of tsunami generation is inversely proportional to the splash that's generated at the source zone. Then we have these kind of odd sources. I term coupled sources. So these they can only generate tsunamis under the right conditions, moving basically at a velocity against square root of GH, and over a certain distance, sufficient distance or duration. Think of it as fetch, if you're familiar with the term fetch in terms of generating regular ocean waves. So those are the coupled sources. And then we have our earthquakes. We can lump in volcanic earthquakes with regular earthquakes. It's the same sort of tsunami generating process. These are our most efficient tsunami generating sources, and most often observed, 70-80% of the tsunamis again. Then we have caldera collapses. I have no idea what to do with caldera collapses. They're kind of beast of their own. I try to lump them with earthquakes, but they're not moving fast enough as earthquakes. But anyway, that's the talk. A lot of people helped out on this talk, bounced a lot of ideas with one of our brilliant postdocs, Kenny Ryan here at the USGS, Ann Rosenthal, and Christy Ryan, who's part of the organization of this wonderful evening lecture series. A lot of people dedicate a lot of time to making this series possible. And I really presented the research results from a lot of different studies, and a lot of people were PIs on these studies, such as Jerry Wazorek. So thank you for your attention, and thanks for coming out tonight. Appreciate it.
Thank you, Eric. That was a great talk. And now, if anyone has any questions, you can either line up behind one of the mics, or I can also bring you a mic as well. And we'll go ahead and open it up.
I'll wait for these guys to walk out.
Has there ever been a tsunami in the Bay, in the San Francisco Bay?
Yes, absolutely. Probably the biggest was 1964 from that Alaska, the magnitude 9.2 Alaska. It did, in 1964, $1 million of damage inside the bay. That's not outside the bay, that's inside the bay. It did some damage to Berkeley Harbor and some other locations I'm forgetting right now. But even the 2011 Japan tsunami was observed in the bay. There's some interesting video on YouTube of the tsunami going towards Emeryville. So certainly, they're not as big. The bay is very shallow. The waves move very slowly, eat up a lot of energy. But tsunamis do make their way into the bay. And one thing maybe was obvious, I didn't explicitly mention it, but we can have mega tsunamis. But tsunamis don't depend on how high they are. We can have micro tsunamis, which we study too, but that just doesn't make the news.
That was wonderful. The meteotsunamis, what's the relative frequency of these things at an amplitude that's damaging?
That's damaging, yeah.
I mean, what we often refer to on the West Coast as rogue waves, how many of those are meteotsunamis?
Well, on the West Coast, not many at all. I was looking in the catalog, and there's a few up and around Puget Sound region, and there's one in 1910 in San Francisco that might have been a meteotsunami. So the conditions just aren't quite right. On the East Coast, that was actually the focus of our study, is to get at the frequency of meteotsunamis in general. Damage involves risk, which is another calculation, but they're actually pretty frequent, but they just don't get very large. I don't want to get into probability, but if you look at a distribution tail, it falls off very quickly at higher amplitudes. So in terms of what you said, damaging waves, those are much less frequent. But if you look at smaller meteotsunamis waves, they're surprisingly more frequent than regular tsunamis.
What's the advice then to people who are in coastal areas or shallow harbors or things like this? Or any idea of risk?
Yeah, in terms of if you have a small boat tied up in a harbor, that's a good one. I mean, for regular tsunamis, the advice is you usually get hours of warning, and you can take your boat not very far out and avoid a lot of the damaging effects inside the harbor. But these, it's hard to tell which weather's turbulent, and it's hard to tell which one's going to generate a meteotsunami and which one isn't. So it's a good question to keep in mind. I mean, Yeah, I don't have a good answer, unfortunately, for you.
Thank you.
So thank you for the talk to your left. So I actually had never heard about atmospheric tsunamis before, so that was interesting. But to the asteroid that hit the Yucatan,
Yeah.
That was about 10 kilometers wide. So are you saying that the depth of the water there must have been more than 3 times that, or did the asteroid effects not have the same effects as the earthquake effects that you said if they're 3 times the distance
Yeah.
or the depth?
Yeah, so the water depth it hit in was very shallow. In fact, half of it was on, well, I don't know what the coastline was back in the Cretaceous there, but it was in shallow water for sure. It was on the shelf. So it would have generated long waves, but like that simulation, a lot of it goes into splash, a lot of it, the energy. In fact, that simulation showed only about 20% goes into the ocean of that energy, and only 1% goes into generating surface gravity waves. So, it's hard to speculate. There's these tsunami deposits that we've seen that are, I'm not a geologist, they seem pretty convincing. Some say they might be storm deposit, but the timing seems too coincidental. I think we just don't know if they were caused by triggered landslides from the impact or from the impact itself. I think, at least in my mind, we just can't tell at this point.
So, but normally would it have the same impact, a 3 to 1 ratio as an earthquake under normal circumstances?
Any tsunami source to generate long waves has to be ideally 3 times greater than the water depth. Everything in hydrodynamics is relative.
That's right.
So irrespective of what water depth you're at, it has to be 3 times the water depth.
But I guess because it was shallow and it just splashed,
yeah,
the mechanics were different.
If something's generated in very shallow water, the reverse of shoaling amplification happens. You get de-amplification as it goes into deep water.
Okay.
But then as it goes back into shallow water, it'll go back to the same height. So there's virtually going to be no amplifications for a shallow water tsunami source.
Okay, thank you very much.
Yeah.
This is neat as an overview. I'm David Morrison from NASA Ames, and I'm the chief scientist in the group that's been doing the asteroid,
great.
Which is, I'm sure, Darrell Robertson will be very glad you used his image. But you might be interested in the result. We had a workshop, and Darrell's work was part of it. NASA, NOAA, people from FEMA, DHS, and the various our Department of Energy labs put together to try to figure out if the tsunamis from relatively small impacts in the ocean were a significant risk. We know what happens when an asteroid hits the ground.
Yeah.
And the conclusion was they are not significant.
Okay.
They're down an order of magnitude, in spite of all the wonderful Hollywood movies that show gigantic asteroid-produced tsunami. It'd still be a mess if it hit near the shore, of course.
Yeah.
It'd be a big splash like a landslide. But we aren't worrying about something going in the middle of the Pacific and coming and hitting San Francisco.
Right. Well, I don't know, maybe you can help answer the Chicxulub question?
None of the people that I was working with are looking at that. Fortunately, we know there are no asteroids as large as Chicxulub out there.
Yeah.
So we've been dealing with things that are orders of magnitude smaller, like 100 meter.
Right. Thank you for that, by the way. That's great to have you here.
I didn't get the scale on the tide gauges.
Okay, let's see. Let's go to the 2004 tide gauge record. That's probably our best one because it shows the scale and the time. A lot of times the raw records, it's really hard to make out the time markings on there. But so this is hours after the earthquake. We put T equals 0 here at the time of the earthquake. Usually it's just the local time of day marked on here, and then amplitude here. 0 presumably is usually mean sea level.
Okay.
And then amplitude above that in meters.
So is this stuff all computerized? Can you?
Yeah, it is now, and thank you for that because you can go on, let's see, you search for NOAA tsunami tide gauges, and what I do and what anybody in the audience can do if you hear of a tsunami warning somewhere is to, in real time, sit at your computer and look at these stations and show the tsunami coming on the tide gauges. It shows you the ones with the tide and the ones with the tide removed, called the residual. So you can watch, certainly in the U.S., and there's other sites with worldwide tide gauges, you can watch the tsunamis as they come ashore at these tide gauge stations. So, yeah.
So has anybody gone and looked in all of the old data to see if there's anything interesting that they didn't notice before?
Yeah, I mean, certainly there's a whole group led by this person by the name of Professor Kenji Satake Sensei now in Japan, who's a fairly famous tsunami, and he was known for inverting all these waveforms to get at what the source was like. That's how he's famous. So he's been doing that for decades now, and it's especially important for areas where we don't have earthquake records and for non-seismic tsunamis. So yeah, this is an important field of research.
Do any of the offshore buoys help in this?
Yeah, so the offshore buoys I didn't mention. Since especially the 2004 Indian Ocean tsunami, there's deep ocean pressure buoys put out by NOAA specifically for tsunami warning. They're recording the tide. They're very precise and accurate instruments to record the very clear signal of the tsunami. They really help in real-time tsunami warning. But you could, and people, especially for the 2011 Japan tsunami, they're using those buoys records as well as the tide gauge records to invert for the source process of that massive earthquake off of Japan in 2011.
Thanks.
Yeah.
For your Meteotsunami, you said it was 1 centimeter per millibar.
That's.
Is that measuring from standard sea level pressure, and is it going deflecting up or down?
Well, it's inverted. You know, the increase in pressure is going to result in a deflection of the ocean's surface. I think that's a rough conversion. Probably depends on pressure, temperature, and a bunch of other things. I just threw that to get an order of magnitude scaling of the pressure effect, but I'm sure there's a lot of other variables in there.
Okay.
Yeah.
One of there's, again, it probably was a Discovery Channel show from years ago. Some island in the Atlantic that has like a third of the island is slowly slipping off. Has there been any further study on such a large landslide that could be generated by that? Yes,
there's been a lot of studies of that. That's from the Canary Islands, Cumbre Vieja Islands in particular. The hypothesis was there's going to be a huge landslide fall into the ocean and create this large mega tsunami belt, travel across the Atlantic and potentially affect the U.S. East Coast. It was an interesting, thought-provoking study for sure. Since then, volcanologists have looked at the volcano more. I can't really report on that. In terms of hydrodynamics, people are using more sophisticated, I would say, hydrodynamic models than in that initial study, showing that the amplitude, especially on the U.S. East Coast, is smaller than what was originally predicted, but still pretty significant. I mean, even for a comparison, a half a meter tsunami is going to knock you down. Think of crossing a half-meter river up in the Sierra or something like that. So it's, I think around the estimates, maybe 1 to 2 meters from a hypothesized event, if those source parameters are correct. But that's a whole other area of controversy. But that's still significant on the U.S. East Coast, especially because the coastal plain is pretty flat there. So it's down a little bit, but still of interesting concern, I would say.
Thank you.
It's analogous in many ways to the asteroids. You produce an impact in the middle of the ocean, and it doesn't propagate.
So that is correct. Landslide tsunamis are similar to asteroids in that they're generating shorter wavelength waves, and if they're tall enough, they're going to maybe break at the continental shelf edge. It's actually given a name called the Van Doren effect, thought of years ago, and now we're just revisiting it. So yes, you're correct. They might break at the continental shelf edge as well.
Have you looked at any of the Hawaiian cliff failures, and is there usable data there? I think when I was down the island, I remember seeing run-ups of 100, 150 meters, so it would seem like those are pretty big events.
Yeah, so those were, I actually haven't modeled those events, and actually I think they were discovered by USGS scientist George Moore, is that right, Helen? Or is it, you don't remember, yeah. But yeah, those were significant events, and supposedly they've seen some tsunami deposits from the Hawaiian Islands from those events. I had a whole talk worth of other case studies I was going to talk about, but one of them was a Hawaiian example but this was a volcanic earthquake tsunami from 1975, the Kalapana tsunami, which I did model, and that's a complex event involving a slip on a fault, but also kind of collapse of the area around Kilauea volcano as well. So it was a very complex event, but a volcanic tsunami that involved an earthquake in that case. The tsunami run-ups from the 1975 Kalapana event weren't nearly as large as what you were talking about here, but still significant. It was measured on the west coast here. Yeah.
So I was kind of interested in the derecho that was coming. Okay. I was kind of interested in the derecho that came across the country and ended up at Moss Beach. Is that what you said?
The derecho started in the Midwest and moved in the Northeast United States. Kind of ended up going off the continental shelf edge off into New England, up into Canada.
Well, I thought it ended up at Moss Beach. Did you mention?
Yeah. So I went through things pretty quickly there. Okay. So there was a submarine landslide tsunami in Monterey Bay from the Loma Prieta earthquake in 1989 that did generate a small tsunami run-up of 1 meter at Moss Landing, kind of halfway around Monterey Bay there. They had a lot of liquefaction, which was more the problem from the Loma Prieta earthquake. But there was a little tsunami there.
Okay, because I was kind of interesting because I actually know two people one that just bought property and one that also did right around there. It's quite funny because the one who just bought something in Pacifica, which she kept talking about liquefaction or whatever it was, and that it wasn't going to be a problem because of where she bought it. And I'm thinking, wow, so what actually happened right there?
Yeah.
Is this a good idea, to buy beachfront property?
Yeah. Well, that's one of the questions, unfortunately, we can't tell specific, property questions of,
But you sort of wonder, because it's a small area. I mean, it was pinpointed, and I wondered how,
Yeah, I don't know if you saw in that simulation, but that tsunami was really resonating. It was going back and forth in Monterey Bay. One of the curious things I've always wondered about, and this happened in the 2011 tsunami, is we saw the damage in Santa Cruz. Monterey doesn't seem to have the big effects as Santa Cruz does. For some reason, there's something about the wave resonance in Monterey that Santa Cruz gets the brunt of it and Monterey doesn't. I don't understand that. But I did want to mention, for hazard purposes, the state of California has tsunami inundation maps online. So if you're interested in any part of the coastline of any populated part of the coastline of California, you can go to the California Geological Survey website and pull up those inundation maps, and you can see that's kind of the worst case scenario. If you have any questions about that.
Okay, we'll go ahead and take one more question.
I get the last question.
Yeah.
Do tsunami waves dissipate on their own?
Yes, once they're generated, they dissipate very quickly in the open ocean. They got a lot of energy behind them. They start dissipating once they hit land. This is a whole part. Well, here we go, the tide gauge record. So here's hours from the earthquake. You can see after 12 hours, the tsunami wave activity is still going on. This is characterized by an exponential, I'm getting a little technical here, but exponential envelope with a decay time of about 22 hours, in the Pacific, 22 hours. So from the 2004 Indian Ocean tsunami, we saw tide gauge records in India going on for over a day. The tsunami waves were keeping going. But they gradually, exponentially start to decay. But it's important to realize first wave is not the biggest. It looks like in Maldives, it was the biggest here. In Phuket, Thailand, for some reason, it's often the third wave, and people have been wondering about that. So this isn't the first wave coming directly from the source. There's some kind of coastal interaction going on to make and that's tragically what happened in Crescent City in 1964. People came back too early and were caught in the tsunami from 1964. Because these are long period, as you can tell, going on for 45 minutes or an hour between waves, so it's easy to get caught in and go back too soon. So it's always best to stay away.
Okay. Again, I want to thank everybody for coming tonight. And if we get another round of applause for...
Thank you.
Thank you.
Fascinating talk.
Oh, thank you for coming. Yes.
Quick question.
Sure. Yeah.
Is it standard to use the term